Hey guys, we're back for more AP Calculus. This time, what are we looking at today? We're looking at 5.3. We're looking at the graphs of f prime, and f double prime. Right now, for this assignment, we're going to be looking specifically at f prime. Let's have at it with another zombie movie. So we've got a movie called White Zombie, and yes, that is where, if you remember the White Zombie band, this is where they got their name. But the White Zombie is a 1932 pre-code horror movie, and it's one of the first zombie movies really out there. Bela Lugosi, who you might know as Dracula, happens to play, a zombie master named Murder. And the important part about this is he tries to zombify a young woman, of course, a young woman, and that's pretty much all we need to know for this one right now. The movie basically follows this woman turning into a zombie. I think you can see her back over here, and these are his zombie henchmen out to do his bidding. So we'll get into that in 1 second with our context. Okay, let's see what we got here. We got the graph of a continuous function f shown in this diagram right here, this graph right here. We're going to use two different highlighter colors to find intervals where f is increasing and where f is decreasing. I shouldn't have said decreasing and increasing. I should have said when f prime is greater than 0 and when f prime is less than 0. So let's take a look. Can we figure out where f prime is greater than 0? Yes, that should be synonymous with every place where the function is increasing. So from a to c1, definitely our function is increasing. From c1 to c2, our function is increasing. Now from c2 to c3, the y-coordinates are getting smaller. So in fact, we have an interval of decrease. From c3 to c4, the y-coordinates are getting larger. So this is an interval of increase. And then from c4 to c5, y-coordinates are getting smaller. So we have an interval of decrease, which, just to remind you, the derivative is negative. And then finally, from c5 to b, we've got an interval where the derivative is less than 0 because the y-coordinates are getting smaller. Okay, so note what happens to the derivative at local maximums and minimums. Where are the local maximums and minimums? Here's a local maximum. Here's a local minimum. Here's another local maximum. This happens to also be the absolute maximum. And hopefully you've noticed that at all three of those places, the highlighter changes color, which means that the derivative changes sign from either positive to negative, which would be yellow to blue, or from negative to positive, which would be from blue to yellow. So summarize that. At the local minimum of a function, the slope of f, which is the same thing as the derivative, that changes from positive to negative. And then at a local or relative minimum, the derivative changes from negative to positive. So negative to positive is a minimum, positive to negative is a maximum. So that gives us our idea for the first derivative test. So the first derivatives test is exactly what we did. If the derivative changes from negative to positive, that means that's a sign of a local minimum. Okay. There's another couple of possibilities, like if you have the left endpoint and the function increases from that left endpoint, and that's going to be a local minimum. And if you have a right endpoint and the function decreases to that right endpoint, something like that, then we'll get a local minimum. Now for a local maximum, there will be a local maximum at C if the derivative changes from positive to negative, or if we got a left endpoint, that means that the derivative is the derivative is negative immediately to the right of the left endpoint, like that. Or the derivative, if you have a right endpoint, the derivative is increasing directly to the left of it. So something like that. Now, just because the derivative changes from negative to positive or from positive to negative doesn't mean that it has to be a local maximum. Okay? It's just that at every local maximum, the derivative does change. There is a possibility that you're looking at a point of discontinuity. So the function still needs to be continuous in order for it to be, let's rephrase that. The function f must still be, it has to be continuous at C in order for us to have a local minimum or a local maximum. If the function's not continuous at C, then of course that's not a local minimum and it's not a local maximum. So that brings us to our first problem of the day. Find and classify all local extreme values of f of x equals x cubed minus 27x plus 3. Note, change margins to be thinner. I think that's kind of like a typo. I think I was just trying to, I think I typed that in there just to remind myself of what to do as I was typing these out. So that's not actually a direction for you. So sorry about that. Should have taken that out. So, all right, let's get going. Notice that there's no interval here. So this is going to imply that we're looking for an extreme value over the entire domain of x. F of x happens to be a polynomial function, and we can say a heck of a lot more. It's a positive cubic function, a positive odd function. So we know it's going to have a one local maximum and one local minimum, or none at all. So first thing we're going to do is we're going to look for the derivative and the critical values. What is the derivative of x cubed minus 27x plus 3? This factors nicely into 3 times x minus 3, x plus 3, which means our critical values are 3 or negative 3. Next, we're going to complete a number line over the domain of f with critical values over the number line and the sign of the derivative under the number line. We should have done this in class, and we did this in the last video. So let's see what that looks like. You'll see that we have our number line. Here's negative 3 over here. It might be hard to read, but that's negative 3. X equals negative 3. Over here, that's x equals 3. To the left of negative 3, if we substituted, for example, negative 10, we would definitely get a positive number. Negative 10 squared is 100. 3 times 100 is 300. 300 minus 27, yes, that's positive. So we got a positive over here on the left side. I think before we were highlighting that. That's positive here. Somewhere between negative 3 and 3, that's a good number to substitute there is 0. And if you substitute 0, you get 3 times 0 minus 27, which is negative 27. So this entire interval is negative. Remember, it has to be negative in that entire interval because there are no critical numbers in between negative 3 and 3. We solved that algebraically. And then how about from 3 to positive infinity? If I substitute 10 here into the derivative, we get 10 squared is 100. 3 times 100 is 300 minus 27. Yes, that's a positive number. So that's positive. So we have that familiar look here. At -3, the derivative changes from positive to negative, which is indicative of a relative maximum. And then at +3, the derivative changes from negative to positive, which is indicative of a minimum. Also, notice that we're looking at a cubic function, so we should have known that the shape is probably going to be something like this. A positive cubic function usually looks like this, unless it's kind of collapsed and you have a double root. Write a summary. According to the first derivative test for local extrema, f has a relative minimum at x equals 3 because the derivative of f changes from negative to positive, and f has a relative maximum at x equals -3 because the derivative of f changes from positive to negative. I'm going to say this again. You have to have a good way to summarize this, so you might as well not reinvent the wheel and just use the sentence starter that we have here. Okay? Whenever you're asked to explain your work, and even if they don't ask you to explain your work, you should explain your work. You're going to use an explanation. Hopefully, just use this exact same sentence starter. So that's really it for this section. We're just doing the first derivative test for local extrema. And we saw how the first derivative works with the graph of f. So, important ideas, that first derivative test. Here's your 4-part plan. First thing you want to do is find critical values. Then you want to locate intervals of increase and decrease on the domain of the function. This is something that some students forget about. You can only really look at intervals that are in the domain of the function. And lastly, you want to classify those critical values as either maximum or minimum, depending on whether you're seeing a change in the derivative from positive to negative or negative to positive. Remember, the function has to be defined at the critical value for that critical value to be a relative extrema. And then to summarize, you want to make sure you use that sentence starter. Don't reinvent the wheel. Use the same sentence over and over again. Calculus has been studied for, well, AP tests have been given for about 80 years at this point. 80 years? Okay, maybe 70 years, maybe 60 years, something like that. At least half a century. So you don't have to start all over from scratch. You don't have to be an Isaac Newton. You just have to stand on the shoulders of the giants that came before you. I like that. Okay, let's take a look at the Check Your Understanding. Madeline Parker, the young bride from White Zombie, is tragically poisoned 30 minutes into the movie and reaches full zombification around 50 minutes. Her hit points throughout the movie is represented by the function hm equals 0.0042 times the quantity x cubed minus 85x squared plus 1074x plus 17,280 in percent living. Now, I admit that's kind of a weird function, but whatever works, works. Where the negative values of this function are going to represent the zombie state. So what are Madeline's maximum and minimum hit points during the movie? So at what time do these extrema occur on t between 0 and 67 minutes long? White Zombie is about a 67-minute movie. You can use your graphing utility to help you. So if you take a look at this, I already have the answer key up here, and we'll just talk about how to get all of these answers. So the first one is to find the critical values. So the critical values happen when the derivative, first of all, we find the derivative here. And one good tip that you might want to think about is if you are taking the derivative and you have a constant that has not been distributed, don't bother distributing that constant. Just leave the constant on the outside and take the derivative of the inside. So what is the derivative of this inside? Well, that is 3x squared minus 170x plus 1074. And then you keep that 0042 on the outside and set that equal to 0. So, since we have a graphing utility, we can graph this derivative to help us find out where this derivative is equal to 0. Here's my calculator, and I'm going to go to the y equals menu, and you'll notice that I've already kind of typed that out inside my y equals menu. Now all I have to do is analyze this function, and I'm going to do it graphically. Later on in the class, we'll probably take a look at this using the solver, which I'm sure many of you are very interested in learning how to use. We will learn how to use that, but right now we're going to do this graphically. So let's take a look at this graphically. Notice that we have a window of 0 to 67 minutes, and that's our independent variable, which is going to be x. And actually, there's a little bit of a mismatch here because this is t and that's an x over there. We'll overlook that for now. And what you can do is use that to go ahead and set your window. We're going to go from 0 to 67. Now, we already know that the derivative is going to have positive parts and negative parts. So our window for graphing the derivative has to include some negative to positive. Now, I already graphed this, so I know that this window is probably way too big. And I'm going to actually decrease this to negative 20 and positive 20. How will you know? Well, actually, you won't know. If you have some sense of the function, like if you have a trig function and with an amplitude modulation, then you'll be able to kind of figure it out from there. Or if you have some sense of how this graph is going to go, you can do that. But otherwise, you're just kind of guessing and hoping you get a window that kind of works. So let's go ahead and graph this. If I set the window on the window screen, I want to push the graph button next. So let's push the graph button. Let's take a look at our function. Okay, this is h prime. And yeah, I think this is a pretty good one. This is this right over here is where the derivative equals 0. This right over here is where the derivative is also equals 0. We can also see that the derivative changes from positive to negative to positive. Remember, this is a graph of the derivative. So let's put this on the screen. So we are looking at the graph of h prime of t. I've just changed it to t to help us out. Now in this part right here, and this part over here on the right, h prime of t is greater than 0 because the y-coordinates are positive. And if the y-coordinates are the same thing as h prime, that means h prime is positive. Likewise, this central section right here, h prime is less than 0. Back to the calculator, this means that wherever this is, that's going to be a relative, let's see, positive to negative, that's a maximum. And over here, the derivative goes from negative to positive, so that's a minimum. We just need to find out these critical numbers. So the correct way to find it is to go second, calculate. You can tell you're in the calculate menu because it says calculate in the top. Also, the blue button over here does say calculate. And we want to calculate the 0, so I'm going to push the number 2. And it's going to ask you a series of 3 questions. If the 0 is here, give me a number to the left of that 0. And you can just type it in if you have some sense of the scale. And I know 5 is to the left of the 0. Now notice that it kind of gives me this bar, this vertical bar. And if you're not quite sure if that's to the left of the 0 and you want to start over again, just second calculate again and look for a 0. And let's go a little bit further to the left bound. Let's just make that 0. How about a right bound now? This is a question, right bound. All right, so a number to the right here, I don't know, maybe about 20. Let's just type 20 and see if that... Okay, so there is a left bound here, there is a right bound here. Is the 0 in between those two vertical lines? Yes, it is. And the last thing to do is take a guess. Now you can kind of cursor over. And the reason why your calculator asks for a guess is because it's going to find the 0 that is closest to your guess. So closest to that. It should be right around 7. Last thing you're going to do is press enter. And it's going to tell you the 0 is at 7.24357. Use 5 decimal places for everything you do. Don't round and don't look back. Now, how about this one over here? This 0 right there. We'll do the same thing. We'll second calculate a 0. And let's figure out what's a number to the left of this. And 20 was right about here. So I'm guessing 30 would be right about here and 40 is here. So let's try 40. And is that vertical line to the left of the 0? Why, yes it is. Now to the right of the 0, I'm not sure, maybe 70? Let's change that to 70. We'll type 70. Oh, invalid. Don't push quit, push go to. Go to will allow you to fix your error, usually. So 70 is too far off the scale. So why don't we make this 65. Okay, there we go. So now is a 0 in between these two vertical lines? Yes, it is. And let's take a guess. Maybe, let's see, this was 40, so maybe right around 50. We'll take a guess of 50, and lo and behold, we got 49.423. So that's how we find the zeros of the function using our calculator. Going back to our notes, we see that it's already there. X equals 7.24 and 49.423. We can make our graph here, our number line. We know that for values to the left of 7.243, the derivative is positive. H prime is greater than 0, meaning the function is increasing. The derivative might be decreasing, but if h prime is decreasing, that doesn't matter. What matters is that if h prime is positive, h is increasing. Here, between 7.243 and 49.423, h prime is negative, meaning h is decreasing. And then from 49.423 to t equals 67, h prime is positive, which means h is increasing. So classify, that means we have a relative minimum and a relative maximum at x equals 49.42308. Finally, summarize. According to the first derivative test, Madeline's HP has a relative maximum of 88.11502 when x equals 7.423. How did I figure out that number? I used my calculator. So let's get back to our calculator here. We'll go to the y equals menu. And here in y2, I'm going to type in the function h. Now that h is in y2, we're going to quit to the home screen and we're going to evaluate y2 at our critical values. So to evaluate that, we're going to call up y2. To do that, you're going to push alpha trace, and notice that we have y2 over here. So scroll down and push enter. That'll put y2 on your screen. And then you're going to use function notation, put a parenthesis there. Go ahead and put the number into the function y2, push enter, and that will give me my negative 69.473. So now that we have that number, we know that Madeline's HP has a relative minimum at negative 69.47325 when x is 49.42309 minutes, because the derivative changes from negative to positive. So that is where we're going to leave things. This first derivative test is really important to you. So really get yourself a good grip on this. So that's the end of section 5.3, day 1. There's going to be a day 2 tomorrow where we get a really good look at the second derivative. We looked at the first derivative today. Tomorrow we're going to look at the second derivative. Have a great day and good luck on your homework. See you next time.